Hi there, I'm Adam Wise, application scientist at Andor, and welcome to my short course, Introduction to Raman Spectroscopy. And welcome to day one, which is an introduction to Raman spectroscopy. So this short course will consist of 4 presentations. Day 1, the basics, that's the day that you're in. Day 2, applications, what do people do with Raman spectroscopy? Day 3 will be a lecture by my friend and colleague, fellow application specialist at Andor, Shane Harrell, on characterizing low-dimensional materials using Raman spectroscopy. Day 4 will be me again doing the Raman spectroscopy of conjugated polymers, which is work that I did in graduate school. I don't expect you to be necessarily that interested in the materials themselves, that is to say the conjugated polymers, but the techniques and the approach that I use might be of interest to your own work. So if you're new to Raman spectroscopy, that is to say you're someone who perhaps has been doing some other optical technique and you're wondering what all the buzz is about, or if you're a graduate student embarking on a new project or anyone else who's just interested in the field, this will be a fairly high-level overview with some more granular breakdowns of specific problems. If you've been doing this for a while, perhaps you might get some new perspective, but a lot of this information might be old to you. That's okay. You might come along for the ride anyway. First, some introductions. Who are we? So, Andor is the company I work for. It was established in 1989. It is a spin-off of Queen's University in Belfast from the physics department, I believe. It has a headquarters in Belfast, R&D in Finland, all over the world, Finland, Toronto, and Zurich, all over the world. There's about 300 or 400 employees, and we are leaders, more importantly, in scientific imaging, spectroscopy, microscopy systems, and analysis software. And we're part of the Oxford Instruments Group. How did we get here? So here's a timeline of innovation. You can see it goes from the late 80s to the current day. I became a user in about 2005 in graduate school, and I became an employee around 2017, so closing in on 4 years ago. You can see here, I won't go through it in detail, but we have many firsts, including, perhaps most importantly, the world's fastest EM-CCD launched in 2012, the ubiquitous IXON camera, IXON. And I will maybe call out some other things, but for the moment, let's keep going. So what are the products that we make? Most relevant to this presentation, we make a lot of different spectroscopy solutions. That is, spectrometers, cameras, accessories, things for recording, high resolution, and weak signal spectra. We also make low light imaging cameras. I can see a Balor there on the left. Let me try my laser pointer out here. I can see a Balor, an IXON, and a Xyla. The IXON and the Xyla are almost everywhere in laboratories. It's possible you have one in your own lab today. We also make the extremely popular ITIS and Newton cameras. Where's a Newton? Here, the Newton. So these sort of soft rounded rectangles you might see attached to a spectrometer. If you have one and you're not using it and you want to know what you could be doing with it, shoot me an email, a.wise@andor.com, if you have any questions, in general as well. I'll be doing questions and answers at the end of this presentation as well. We also sell optical cryostats that go great with our spectroscopy solutions and low light cameras, and also microscopy systems, confocal microscopes, principally the Dragonfly. So who am I? I'm the Senior Americas Field Applications Specialist at Andor. What does that actually mean, that job title? It means I work with scientists and engineers to identify the solution to their technical problem. My background is in a number of different spectroscopy types, generally optics and metrology. So I received a PhD in using a Raman-related project in 2012, and I've been in various roles in the optics metrology ecosystem since. And I just want to thank, I'm not sure if I have acknowledgements here, but my PhD advisor, John Gray. So I didn't just receive a PhD from thin air. I worked in this group and had a fantastic time and learned a lot doing it. So if I don't do acknowledgements in the first slide, I just wanted to point that out. And I'm currently based outside of Philadelphia, so if you're in the northeastern US, chances are I'm not too far from you. So who are you? And you're whoever you are, and that's totally fine, but this is just sort of where I was aiming this. You're maybe familiar with microscopy or some optical spectroscopy techniques. You're new to thinking about Raman, and you want to know how the sausage gets made. And I'm not sure how well this phrase goes cross-culturally, but you want to know in detail some of the very granular, low-level, potentially ugly background logistics of how these things work. I'm going to try to include as much of that as possible more as we go forward. The first presentation today will be fairly basic, or at least I'm trying to keep it basic. And most importantly, you're curious to see some odd Raman applications and tricks and new ways of thinking, perhaps. And maybe you have some of our equipment and want to discuss how to use it either on a current project or a new project. I wouldn't be surprised if that's a fairly large fraction of the audience because our equipment lasts for a very long time and it survives multiple generations of students and postdocs and maybe even gets handed down from one primary investigator to another, principal investigator, PI, to another. So you can inherit the stuff and you may not know what it's capable of. And if you want to talk about that, we're absolutely happy to talk about that. So again, feel free to email me or one of my colleagues. And as an aside, I can't encourage you enough to check out the Andor Learning Center. And the link is up in the slide here. I'll try to link it separately as well, but it's easy enough to search for. We have a ton of additional articles, talks, application notes. I have some external speakers for this course as well who are contributing Raman-related talks that will show up here shortly. It's not just Raman-related content though. There's something for everyone here. And I think, in my opinion, it really fills in the missing middle between vague introductory stuff that doesn't cover enough of the details and nitty-gritty, and then on the other end, original novel research, which glosses over lots of basics and gotchas. So there's a lot of great stuff here. I do encourage you to check it out. So what am I hoping for as the outcome of this course? So this is a short course that will probably be about 2 to 3 hours total length of actual presentations, more including questions and answers and overhead and so on. So because this is only a few hours, it's not really a replacement for a full-length course or textbook. This is merely the appetizer. So if I whet your appetite, you will seek out some more of the references that I throw up here. So maybe I can transmit a new perspective or give you some clues about the work that you're doing or the work that you're embarking on or the work that you may be embarking on in the future. Most pointedly in my mind, I'm thinking about a moment I had with one of Falstad's math and physics applets. If you've never experienced this guy's work, it's really fantastic. I recommend you click on this or type in the URL if you can't click on the video and mess around with them. They're fantastic and they're a great way to see something that you may have. I have a physics degree for what it's worth, physics undergrad degree, but it was interesting to see someone make a visualization for transitions in molecules and all these other things. And you can look at it, and even though it's not rigorous and it's not a perfect physical representation of reality, perfectly truthful, you can get a lot out of it as a starting point for these weird ideas. And I think of the term egg of Columbus, which is, and maybe I'll throw up a slide here about what that is, but it's the moment where you realize something and you can't unsee it, right? So some people point out being shown the arrow and the FedEx logo, but I remember thinking about an S to P transition in a hydrogen atom and looking at this animation of this thing bouncing back and forth and saying, oh, I get it, I get it, I get it, I get it. And it wasn't because it was a rigorous representation, like I said, or a problem set that I was grinding through. It was just a new angle shown on something that I was already learning in another method. So that's what I'm going for as well. Will I actually achieve that? We'll see. Let me know if I do or don't. So without further ado, day one of my short course. So very quickly, and if you're only going to stick around for a few minutes for this course, I just wanted to give the elevator pitch for Raman spectroscopy. What is a one-slide, minimal, terse description of Raman spectroscopy? Well, it's an optical spectroscopy method that uses similar hardware and methods as photoluminescence. If you're familiar with photoluminescence, you can do with some modifications or with some modifications in experimental technique, Raman spectroscopy the same way. You zap, well, I'm getting ahead of myself, but we'll get to that in the next slide. Raman spectroscopy looks at light inelastically scattered off materials. So light bounces off and it comes off with not the same energy. Inelastic because of loss or gain to molecular and lattice vibrations in the material that you're looking at. So it is a vibrational spectroscopy. And the Raman spectra that you get, the frequency and intensity of the peaks, where you're losing or sometimes gaining energy, shows which bonds are present, but much, much more. So because you can see molecular bonds, it's non-contact, it's non-destructive, and you can do it in a wide variety of geometries, different colors, different methods. It's used very robustly for materials identification. I would say that's the main application by volume or something like that, by time spent, but so much more. All right, that said, if you're going to continue on, we'll take a closer look at these statements. I just wanted to give you the quick pitch. So Raman spectroscopy looks at scattered light. What does that mean? We hit a sample with a laser at a single monochromatic wavelength, and it must be ideally very monochromatic, very pure, no extra junk, narrow bandwidth. Then we take the light that's scattered off that sample, focus it with hopefully some sort of lens, otherwise it's not going to be very efficient. And we take that original wavelength, and now we're getting some side bands on that, or bands that represent energy lost to the material. We focus that light from the sample onto a spectrometer, disperse it onto a camera or some other sensor. It could be a photomultiplier tube or even photographic film if that's what you have. And then you look at the spectrum. Then you do things with it. I'll show what those are shortly. So here's a cartoon of a minimalist setup. Very cartoony. We'll get into more real setups on day 2, I believe. So here we're showing a laser illuminating a sample, and a little bit of the a tiny bit of the incoming light is scattered off that sample at a longer wavelength or lower energy. So one of the nice things about Raman spectroscopy being a relatively low energy, visible light, often, sometimes UV, sometimes near IR, but close to visible, non-contact method is that we can do it in a way that takes advantage of other instruments for sending excitation, collecting scattered light. So Raman spectroscopy looks at scattering, not absorption like FTIR, and it can work at virtually any wavelength, but it's typically visible or near IR, occasionally UV. And the interesting thing is it can piggyback, or one of the interesting things is it can piggyback on optical tools, for example, microscopes. And here you can see some kind of Nikon microscope. Let me get the laser pointer. This is a Nikon TI something or another, hooked to one of our spectrometers. Here's the Chimera 328 with an ITIS and a Newton attached here. And you can do, if you can measure epifluorescence, you can also measure epi-Raman if you have the appropriate filters and gratings and so on. But there's no high magnetic fields necessarily involved. There's no pressure, there's no x-rays. It's often a low input technique, or a low overhead technique, I should say, that you can gain a lot of information from. And here's another example. If you peer very closely, you can see an Andor camera in here. But this is a telescope for standoff Raman. So looking at a telescope and doing spectroscopy through a telescope. Not the most light efficient, but you can do some amazing standoff detection. And here they're showing this company, and I've linked to their product page here, showing explosive detection in cartoon form with a telescope doing Raman spectroscopy. And I'll explain a little bit more about that later, about why explosives are a particularly popular target for Raman spectroscopy, not for general targeting. So just a quick overview of the origin of the Raman effect. The eponymous CV Raman here, pictured in 1928, or was discovered in 1928. I imagine this was pictured sometime after that. The story is surprising and interesting, full of twists and turns, and I've linked a brief history here. Hopefully you have some access to the original slides so you can see the link. So he experimentally demonstrated it using not a laser, because of course he's doing this in 1928, long before lasers are available, or even a twinkle in someone's eye. But he used a telescope concentrating sunlight aimed at various liquids. And now my question, of course, is how could that possibly work? We'll revisit that later. Now the question is also, why did it take until 1928? Fluorescence was discovered in 1852, if not far earlier. I need possibly a cite for that far earlier comment. But the reason is, or one of the reasons, is that Raman scattering is weak. And how would you even distinguish Raman scattering from weak fluorescence, assuming you could get rid of the fluorescence? So we'll zoom back in on this, but I just wanted to give credit to the discoverer, or at least one of the discoverers, but the eponymous discoverer of the effect. So just a quick comparison, Raman spectroscopy versus photoluminescence. So I've made the point that they're measured often in the same geometry, or can be measured in the same geometry. But I wanted to give you a view of how you can compare the products of the two methods. So as I say, this is how you can measure photoluminescence as well. If you have some excitation and you measure at a longer wavelength, the emission coming out of there. So what makes Raman different than photoluminescence? Well, first of all, and this probably can't be overstressed, is that photoluminescence is generally a very, very strong process. So you shine a laser, a blue laser into some fluorescein or something like that, and it will glow. It will glow like crazy. You can see it with your eye from across the room. Raman is a very, very weak process in comparison. So depending on the exact molecule, I believe, and of course this varies, it's in the range of 1,000,000 to 1,000,000,000 times weaker than fluorescence. So if you have a billion fluorescence photons coming off in some process, you might have 1 or 100 Raman photons coming off. So as you can imagine, photoluminescence wins when they're both present and overlapping. So second, Raman is relative to the laser line. Photoluminescence is usually at a set energy. So that is to say, if I were to vary my lambda naught there, the wavelength that I'm coming in here, it could be blue, it could be red, it could be green. There are certain other things that come in there, but generally, well, what will always happen is that your Raman spectra will shift with the laser line. So if I were to excite my photoluminescent sample with, change the wavelength of my excitation, generally the emission is about the same, whereas my Raman spectra will slide back and forth relative in terms of energy. And I'll sort of show what I mean. I'm describing literally hand-wavingly some of these things. So Raman scattering is faster than PL, than photoluminescence. We'll say what that means. And Raman scattering carries, in my opinion, and perhaps subjectively, much more information. So to give you an example of what I mean here, here's a complicated molecule, PTB-TSB2, and here is its structure over here. It's a monomer, and these are measurements of the polymer. Here is its photoluminescence spectrum in blue, and you can see, as with many organic dyes, it's a poorly resolved, or organic molecules in general, perhaps. It's a poorly resolved, broad, and you can see the x-axis on here. It goes from 650 to 850, so it covers, a large part of the near infrared. And it's blobby. There aren't really very many well-resolved features. So the question is, how much information would I need to characterize the spectrum? Well, I could write down the center wavelength, or the wavelength maximum. I could give it some rating for skew, like it's hilled up in this particular direction, wedged in that direction. And I could characterize that, perhaps fit a Gaussian with skew to it. And I can also include the bandwidth, so it has some very wide bandwidth here. And with those three numbers, and written down on a post-it note, I could probably reproduce the spectrum pretty well. On the other hand, here's the same molecule's Raman spectrum. Technically, this is a resonance Raman spectrum. Don't tell anybody. For our purposes right now, that's okay. But carries much of the same information as the Raman spectrum, so ignore that for the moment. It's a Raman spectrum. And here you see, instead, these units are in Raman shift in centimeters to the -1. What's that all about? We'll go into that in a minute. But you can see, instead of one large, broadly spread out progression, you have lots and lots of small peaks, probably about 20 or 30 overlapping narrow peaks. And we'll talk about what these mean. But if you were to record just simply in a notebook or a spreadsheet, how much information would it take you to record the spectrum? Well, you'd have to go through in each peak and say, okay, here's the center energy, or here's the center wavelength, here's the width, here's the intensity. And you'd have quite a roster of peaks at the end of this process. So you've just literally generated more energy and more information in just kind of my information theory treatment of this. Not that I'm an expert in that at all, but just in terms of how many numbers it takes to characterize it. So I've belabored that quite a bit. I'm just trying to make a point here that there's more information. What that information means, we'll get to shortly. Here's another example. Here's indocyanine green. Here's the structure. It's a smaller, but still fairly large molecule, a dye. Just to show you, I'm not cherry picking one particular molecule. Are they of the same class of molecules? Yeah, they're conjugated organics, but so is so much else, right? But just to give you another view, here's the fluorescent spectrum, photoluminescent spectrum. Here's its absorption. This is sort of the excitation for that fluorescence. And these are both blobby spectrum. Again, I'm just making the point that photoluminescence has a relatively unstructured emission or unstructured spectra associated with it that are hard to separate. They all look very similar. Or, I'm sorry, that's a gross generalization. Many of them look very similar. On the other hand, here's the Raman spectrum. Well, this is a SIRS spectrum, actually, surface enhanced Raman spectrum, but the point stands. This is a Raman spectrum here, and you can see, again, many peaks. What do they correspond to, though? So just real quick, I said what's the word I'm looking for? Incredulously, centimeters to the -1. What kind of unit is that? So Raman involves, like I said, the loss and very, very rarely the gain of small amounts of energy. So a typical unit for a Raman shift, which is how we sort of reckon these spectra, is the wave number. So centimeter to the -1. aka wave number, inverse centimeters, rarely Kaiser. I've not really heard that in the wild, only read it in older books, but just so you have it out there. And you can remember that because E equals hc over lambda, that this is proportional to energy if we forget about this part. I think the main reason that it's used, these units, are that they're proportional to, they're units of energy, and they're in chunks that are a reasonable number to remember, a reasonably useful number, somewhere between 0 and a few thousand. So if we were to work in joules, it would be an unwieldy small number. If we were to work in EV, it would be an unwieldy number. If we were to work in inverse meters, then that would also be difficult to reckon. So how do we go from a real wavelength spectrum to a Raman spectrum? So maybe this isn't the best example, but I thought it was quite cool because it's one of Raman's original spectra of benzene. So the excitation is at 435.83, the line from a mercury lamp. Here I've highlighted it in purple. And we convert to wave numbers for the original excitation wavelength. So to get from nanometers to inverse centimeters, we take 10 to the 7 divided by the wavelength in nanometers, and we get about 23,022,944 wave numbers, or inverse centimeters. There's some unknown band, where is it? Here, and it is about at 457.4 nanometers. So what is the actual Raman shift there? Well, we take the excitation in wave numbers, subtract the unknown band in wave numbers, and we get, although I think my head is covering it, about 1,000 wave number shift. Now let's see if I can show this a little bit more clearly on an X and Y spectrum. Those guys did a lot with photographic film, but it can be hard to read the intensities on there unless you're just very good at looking at differences in white contrast there. So here's one spectrum. This is a resonant Raman spectrum with some fluorescence left over. So green is where we're exciting, and I've gone through great lengths to block off that laser beam because it's so much stronger than the Raman spectrum that it's creating. And you can see the units, these are the real units that we would measure in a spectrometer. My light is at 514 nanometers right here, and here's 550 nanometers, 600 nanometers, 650, so on, units that we can understand. We probably lose the ability to actually see the light around here. So this is the red to the near IR. It's all, I'm not sure if there's any real definition for where the near IR starts. If there's some IUPAC thing, then I'll feel kind of dumb, but that's all right. So again, this is our laser line here, and we would see it for real in the spectrum if I wasn't going through great lengths to block it off using filters and moving the spectrometer away from it. So now this is the same spectrum, same exact data, but now represented in units of Raman shift. So I did the exact same math that I showed on the last slide, just that simple change of units, where I took the excitation, 10 to the 7 divided by the excitation to get our Rayleigh energy or Rayleigh frequency or something like that. So that's 0 because we're reckoning things in terms of energy loss versus the original wavelength or energy, whatever you want to call it. And that's our reference, that's our datum. So we're going to reckon everything in terms of energy shift from that. So we take that x-axis, we go 10 to the 7 over this thing minus, or this 10 to the 7 over this 514, 10 to the 7 over all these numbers up here, and then we create a new x-axis for the Raman shift. So we do this specifically because, as I mentioned before, Raman is always relative to the laser, relative to the excitation energy that you're using. So this happens to be done with 514 excitation, and there's some interesting things that happen as you move the excitation wavelength around, move it up and down in terms of wavelength, not physically up and down. But because this is now going to be invariant with different wavelengths, these Raman shifts are always the same in energy, not in wavelength. So if I were to overlap, say like a 647 excitation or an UV excitation somewhere, in 230 nanometer excitation, it wouldn't overlap in wavelength, but it would overlap in Raman shift. And maybe I should have actually had one of those. That would have been neat, but next time. So a more concrete example. So say we hit a drop of cyclohexane with monochromatic, again, 514 light from a laser, 514 nanometer light from a laser. We collect the scattered light with a lens. We remove the residual laser light with a strong edge or long pass filter, and we focus the collected light onto a high resolution spectrometer. So finally, we record the emission or scattering spectrum, whatever you want to call it. I think scattering is probably more technically correct.
with a high sensitivity camera because you need one for such a weak process to capture one. So you can't use, generally can't use an inexpensive, webcam, or even the nice camera on the iPhone, I think would have some trouble with it because it's not cooled, to my knowledge. So you'd have quite a bit of dark current there. We'll talk maybe about camera parameters tomorrow, I believe, or during the next episode. But again, so here's our wavelength. Again, the laser, which is kind of represented by this clipped, very bright line here, and you can see it's maxing out at about 65,000 counts, which is the max for our 16-bit cameras in general. Again, I would completely block this off because otherwise it will wash out the entire spectrum. And then here is the Raman spectrum of cyclohexane. So you can see we have all of these little sidebands. If we didn't have the sample there, if we didn't have the cyclohexane here, we would only measure the scattered light from the laser and then whatever room light or background light we had that we would hopefully subtract out. But here's our sideband. So we lost this much energy. If we converted that to the same scale, then here are our Stokes shifted bands, they're called. These are the sidebands that lost energy from the interaction with the cyclohexane. So we have all these little sidebands at slightly longer wavelength / low energy than our laser's original value. So you can see here's our, I hope I'm not belaboring this too much, but I really just want to give you a feel for what Raman spectra look like in the wild, raw, before they're processed kind of. So under some circumstances, you might also see higher energy sidebands as well, where the laser has gained some energy from the scattering material. They're rarer, not only because generally the way they're measured makes that impossible to see under normal measurement geometries. Go into that more on day 2. But you only see them at shorter Raman shifts, smaller Raman shifts, even if they are there. I'll explain why probably tomorrow. So again, this is the cyclohexane Raman spectrum, kind of filtered through what you might actually measure, or filtered through the method which might actually measure it. So to compare Raman spectroscopy versus photoluminescence, again, I just wanted to show these two. This is a measurement that I made back in grad school. I'd hesitate to even call it an experiment, but there are 2 components here. So the first is a conjugated polymer dye, polyphenylene vinylene. And you can see here is the undoped. So there's nothing in it. It's just mostly, well, almost pure, and it fluoresces in the green to yellow to red. So this is the photoluminescent spectrum. It looks a lot like the ones that I showed before, a pretty broad photoluminescent spectrum with some structure typical of a conjugated organic. And you'd say, okay, so there's the photoluminescent spectrum. The Raman spectrum is there as well. It's buried, hidden down in the noise here. So Raman and photoluminescence always, or almost always, coexist, assuming there's photoluminescence. But Raman is normally hidden by much brighter photoluminescence. So again, here, this is the undoped, and what we're doing in this experiment is, or this measurement, experiment is a bit generous, we're adding a quenching molecule that has its own fluorescence in the near IR, but what it does is as you add it, it steals the excitation. When you make an excitation in the PPV, it will grab that excitation and shut off that pathway of emission in the green to red. So the more that we salt in this dopant, the more that it quenches the photoluminescence. So as we go down here, and these spectra are all normalized, otherwise this would be, thousands of times brighter, or thousands of times taller, is that as we start to quench the photoluminescence, you can see the resonant Raman spectra emerge. So it was always there, it was always doing its thing there, but now we can see it when we've actually started to shut off the fluorescence. So I just wanted to make that point, is that you're sort of always doing Raman spectroscopy when you're doing photoluminescence, it's just you're not able to recover that signal. So here's one extremely complicated and difficult way to recover that signal when the 2 overlap. So if you can measure quickly on the picosecond scale, you can grab the Raman signal before the photoluminescence actually hits you. So let me show my laser pointer here. So this is the spectrum that they're measuring without a gate, without their cared gate that they're doing here. So this is again a broad photoluminescent spectrum. DCM is a laser dye. Then here's the spectrum with the gate in play. So you can see that this is actually a Raman spectrum. So I believe there's solvent peaks in there as well, but you're actually able to measure a Raman spectrum with a highly fluorescent molecule present. But how? And here's their system. So they're using the Kerr effect to quickly act as an optical shutter to let some light through and then immediately snap shut. So here's the direction of propagation, and you can see, and I just love this diagram. So here's the fluorescence, and then this is kind of time, right? So there's time's in this direction. So our Raman signal is coming right before that, promptly before the fluorescence, and I imagine very vividly, kind of like what's his name, Indiana Jones running away from the front of the boulder. So the Raman is just booking it as quickly as possible, as promptly as possible, ahead of the fluorescence. So if you can snip this time point off right here, you can actually capture the Raman very quickly. I won't dwell too much on this slide more than I already have, because it's unlikely that you'll be able to do this yourself. So for all I know, there's a commercial version of this available, but probably not. There's a lot of, you need a pulse laser, you need this kind of fussy setup. So I say it's not usually practical yet, but it's extremely cool. I just wanted to point that out, that you can do it in the time domain if you can do it, in a very fancy way. And it meaning capture the Raman spectrum ahead of the photoluminescence. Again, a closer look at a Raman spectrum. We're actually approaching what those peaks mean. So we're 29 minutes into this presentation, and I haven't talked about the physical mechanism for what Raman scattering actually is and what we're seeing represented in the peaks. So in short, Raman peaks correspond to molecular, or in a crystal, lattice vibrations that symmetrically change the polarizability. So benzene, that's the molecule that you see there. My benzene in the middle here is looking a little bit unconjugated. That's okay. So imagine this is benzene and not cyclohexane. So benzene has two strong Raman active vibrations that are represented down here, and I'll talk about those in a sec. So light somehow interacts with these molecular vibrations, losing a little bit of energy and shifting to a slightly longer wavelength. So if we can measure and disperse the light from that sample, we can actually learn something about the composition and nature of the material that we're looking at, say in an unknown sample in a mixture. So how are these vibrations, what do these vibrations actually look like? So here is the high frequency vibration at 3000 wave numbers, and you can see that this is the protons around the perimeter of the benzene bouncing in and out, and they're doing it in a very symmetrical way. What do I mean by symmetrical? Well, if you rotated this molecule, if you clicked it by 1/6 of a turn in the same symmetry as the molecule itself, then the vibration would look the same. Nothing would change places, or nothing would change phase, or nothing would go the other direction. Likewise, here's a lower frequency vibration, which is the atoms in the ring vibrating in and out. And you can see this is a lower frequency vibration. These are more massive atoms bouncing back and forth more slowly. And this is a kind of like a radial breathing mode, I think it's called. I might be misusing that term. So somehow the electric field of light interacts with the molecule and scatters off of this vibration, or it interacts with this vibration, perhaps is a better way of saying it, leaves a little bit of energy behind in the molecule, and comes out downshifted slightly in wavelength. And by carefully keeping track of where that energy loss, or the magnitude of that energy loss, and how much of the light loses energy that way, we can say something both about the composition of the sample and about the environment and the nature of the molecule in that sample. So we'll talk more about that as we go. So how do you actually identify Raman modes if you measure, say, an unknown molecule or unknown composition, unknown mixture? How do you actually look at those peaks and say, well, this is likely to be this is likely to be that? How do you map peaks to vibrations to molecules? So for unknown substances, that could be quite complicated. Say you have a mysterious liquid, clear liquid, in an unlabeled amber bottle. Someone was being very bad with their waste handling practices. So typically what you'll do in that case is basically pay for someone else to do it for you. They'll have some linear algebra going on under the hood with a lookup table of stored values. And this is a handheld Raman spectrometer by Ragaku, and this person with the glove here is pointing it at the bottle, getting a quick low resolution fingerprint spectrum, and then that system is going to suggest a best match perhaps for it, or best match of mixes. So otherwise, if you're totally on your own, you can use tables that can provide a good starting point. And here's a link for Raman mode frequency. So you can see, I just clipped the top of it, and I'd recommend you check these guys out, or check this link out. But at the lowest frequency, you have lattice vibrations, and then climbing up, you have at the highest frequency generally hydrogens bouncing back and forth, and so on like that at about 3000 wave numbers. So more limitations of Raman spectroscopy. So vibrational frequencies are mostly shared across molecules, so you may not know whether you're looking at one functional group, on one molecule or another molecule. It doesn't give you a complete picture. You have to disentangle mixtures that might have overlapping peaks. There's not really a great way to do a foolproof ID based on what you see. You might need some kind of hypothesis going in. And there are very few unique bonds, but where they are found, they're likely to excite a lot of interest. So for example, explosives have bonds, nitrogen bonds that are not seen necessarily in the background. So they kind of show up where you could say, you're unlikely to be carrying something else. This is ammonium nitrate or something like that. And we can see it very clearly. It's not going to be present in the grass or in your skin or in whatever. So it's not a tricorder or whatever the Star Trek thing is that you can, point at an unknown substance and always say perfectly, this is what this is, or this is substance A, or this is a mixture of substance A, B, and C in such and such a proportion. But you can do that if you go in with some hypothesis about some assumptions about what you're looking at. So just a quick note about the difference between Raman and infrared absorption. So Raman and IR, aka, or sometimes perhaps typified by FTIR, they're both vibrational spectroscopies. So that is, IR and Raman bands come from light interacting with vibrating parts of molecules, or vibrations in molecules. So IR and Raman are complementary. Raman active vibrations are weak in IR and vice versa. So let's talk about why that might be. And I'll give you a very hand-wavy mechanism for Raman scattering. So imagine we have a jellium molecule, a diatomic jellium molecule. So that is to say, there are some small positive nuclei here surrounded by a jelly-like negative cloud of electrons. And this is not a fantastically realistic picture of reality, but it captures, I think, some of the relevant details of the mechanism at a level that we can kind of just throw out there and then think about for later. So one of the key points of this jellium molecule is that it's polarizable. So if we were to apply an electric field, it will form a dipole in response, which is to say, or it will get polarized, and there will be a dipole in response, which is to say the positive charges will shift a little bit one way, the negative charges will shift the other way, and we'll have a little two-pole system that we've induced there. So a little bit too positive on this side, a little bit too negative on this side. So it is polarizable. It shifts in response to an electric field, creating a little temporary dipole. And I hope I've drawn both the direction of the dipole and the electric field correctly there. I can never remember the convention. So now imagine that this molecule vibrates at some frequency omega. So here I've pulled a few frames from this vibration. You can say, it's here, it gets kind of pulled together, squished, and then it bounces back and forth. So it's literally just going like this, just bouncing back and forth. So the charges move symmetrically, no change in dipole just from vibrating. So you can see that as this thing vibrates, and ignore this for the moment, as this thing bounces back and forth, the center of mass of charge stays the same, stays neutral. There's no net movement of charge. If I were to draw a line through here, there's always an equal amount of charge on one side and the other here in the direction of the molecule, in the direction of the bond axis. So it moves symmetrically. Now, hear me out. What if the polarizability changed a tiny bit as the molecule vibrated? So here is the molecule at this frame when it's squished together. Here's the molecule at this frame when it's pulled apart, and just pulled apart by inertia. I mean, not by some external force, but just going like this. So what if we looked at the polarizability when the molecule's like this, polarizability when the molecule's like that? What if they were just a little bit different? Why would they be different? Well, we could kind of imagine hand-wavily again that here the electrons are squished right up against the protons here, against the nuclei, whatever you want to call them. Here there's a more diffuse zone in the middle, so it might be a bit easier to pull this apart. So if we were to apply an electric field in this direction, we might form a little bit more of a dipole at this moment than at this moment. Okay, well, maybe you'll go along with that ride for me, just for the purposes of argument. So what does it mean now? How do we go back from that to imagine some way where the electric field from light can interact with the vibration of a molecule? And the mechanism for how that works is that those two things interact through the polarizability of the molecule as it vibrates, the change in polarizability of the molecule as it vibrates. Here's a very brief and classical approach to that idea. And even though these are equations, please just hear me out. Again, it's a pretty simple, I hesitate to say that, it's a clever and succinct way of putting this. So the induced dipole mu on the molecule is equal to the polarizability alpha times the electric field E. Okay, so don't think that this is representing anything more than what I just said. So we're just defining, we're saying, okay, there's a dipole mu, that's the strength of that, we're qualifying the strength of that dipole, and we're saying it's proportional to alpha, the polarizability, times the electric field. That's only to say that there's some proportionality between dipole and electric field symbolized by alpha. The polarizability alpha now, it's not steady state. It's changing as the molecule vibrates at frequency omega. So we're going to open up alpha and give it a steady state part, a constant part, and we're going to give it a little component, a small component, alpha sub 1, that changes with the cosine of time at this frequency. So we're saying, all right, here's our static polarizability. What if that polarizability changed a little bit with time, cyclically, as the molecule vibrates? Now, bear with me, the electric field of our laser oscillates at omega sub L at a different frequency, a much higher frequency. So the electric field is some scaling constant, E naught, so some magnitude times the cosine of time scaled by the frequency here. So just a different cosine term happening at a much, much faster frequency. So what we do is we take 2 and 3 and plug it back into 1. So we get mu is still equal to alpha E. The dipole is equal to the polarizability times the electric field, except now both of these are changing with time. This one has a static part. This is the molecule's polarizability, and a time-dependent part. This is all time-dependent. This is the electric field of our laser. We multiply this out, this chunk here, and the relevant part is alpha sub 1. This is how much the molecule is changing with polarizability with vibration, times the magnitude of the electric field, and then the product of these two cosine terms, one dependent on the vibrational frequency, one dependent on the laser frequency. So, and again, not that you're modulating the laser, this is just, the laser's changing electric field with time. If you imagine a visible light laser, that wavelength is very, very large compared to a molecule or a tiny little scatterer. So I imagine myself, I'm a molecule, I'm in the electric field of a laser that's being aimed at me. I don't see wiggles. I see this electric field around me going up and down with time changing direction. So you experience kind of this like bath of that. So this molecule is in a time varying electric field. It doesn't necessarily know it's from a laser. So which through a trig identity, which it's not that obscure because I've heard of it and I'm terrible at math. So which through a trig identity, which you can look up in your table of trig identities for the product of two cosines. If you expand this out, it gives us 3 components. And it's really interesting because each one of these components has a physical meaning. Again, this is a very superficial approximation, but again, it gives us the Rayleigh wavelength. That's the wavelength or the frequency that comes out elastically scattered at the original laser wavelength. And you can see that's the static part or the steady state part of the polarizability of the molecule, the electric field magnitude, and then the cosine of the laser. So this is just, the cosine of the laser frequency times time. This is just the laser now. So this is the same energy as the laser came in, the same wavelength or frequency as the laser came in. We have the Stokes shifted, which is the lower energy Raman sidebands, which are proportional to the change in polarizability, the small component, the magnitude of the electric field, and now the cosine of the difference of the laser wavelength and vibrational wavelength. And then the anti-Stokes, we don't worry as much about this, but this is the higher energy side. You can see that this is the sum. This just pops out of a pretty simple trig identity, and you get something that gives you maybe some idea about the mechanism. So if you hadn't ever heard about the Raman mechanism, you could say, okay, well now I can say maybe confidently, maybe less confidently. It's an interaction of the laser and the molecule's vibrations. And how do they actually see each other? It's mediated through something about the polarizability changing in the molecule as it vibrates. Again, hand wavy. Now here's a very hand wavy mechanism for selection rules. So Raman, there are way more vibrational modes in a molecule than there are Raman active modes. So why might that be? Remember the Raman modes that I showed you, the Raman active vibrations that I showed you in benzene. They were highly symmetric. So imagine we had a stretch that was asymmetric. So here we can kind of see this is a now triatomic linear molecule, and this is sort of the vibrational mode that corresponds to one nuclei or one nucleus bouncing back and forth with respect to the others. So now if you flip this to superimpose these two extremes of the vibration, the vibration's going like this. If you wanted to superimpose this one on this one, you'd have to flip it around 180 degrees. So it's not symmetric there. So again, here's the two extremes up here and up here. Before, for our diatomic molecule, the extremes were just out here and in here. So one could charitably imagine that these have the same polarizability, so you wouldn't expect quite the same Raman activity. But more to the point, here in our vibration, over the course of the vibration, we've had excess positive charge slosh that way, or going the wrong way. Then on this side, where we have excess positive charge slash the other way. So we have positive and negative charges going back and forth. That's a much more direct way to interact with the electric field, because we can simply radiate or absorb time-varying electric fields that way. So this lopsided movement of charge back and forth could make could absorb or emit low-frequency light, so IR activity. So to bring you to a conclusion for today, because I've gone for about 43 minutes, a note about resolution. Just wanted to talk very briefly, and we'll segue tomorrow into actual measurements and actual applications. But Raman spectroscopy demands a reasonably high resolution spectrometer and grading to go with that spectrometer. So this was just to address the point of why can't you make, why would you be unlikely to measure good Raman spectra with a photoluminescence spectrometer, one that isn't quite loaded for Bayer in the same way that you would have for a purpose-defined Raman spectrometer. So this is a simulated cyclohexane Raman spectrum, and this is my spectrum simulator you can play with for using different size and grading spectrometers, different focal length and different gradings in spectrometers. So here's a Chimera 328 with this ITIS camera using 150 line per millimeter grading in blue. That's a low resolution. And then the green is the same spectrometer and camera using a 1200 line per millimeter grading. This is a bit non sequitur since we were just talking about hand waving, but again, we'll segue with this to the next discussion about more practicalities of Raman spectra and applications. So why would you want / do you need a higher resolution spectrometer? Well, you can see here there are Raman modes that you can't even resolve, two overlapping ones with the lower resolution spectrometer. So we'll get into again the requirements and the hardware on the next one. So.
And on that note, that's the end of day one. Thanks for hanging in there with me. In a minute, I'll take any questions you might have, but first a quick note about our next session in 2 weeks, I believe. We've had a somewhat roundabout intro to Raman spectroscopy today, and next time we'll cover more about the experimental practice of Raman spectroscopy, as well as real applications, scientific, industrial, and commercial. And how those two things interweave, that's to say, how the applications leverage unique capabilities of Raman and how they deal with the limitations. So if you're hearing me talk today on April 28th, we're going to have a question and answer session now. If you're seeing this at some other time, feel free to send me an email, a.wise@andor.com. And thanks again for your attention, and let's hear some questions now.
Oh, all right. Hey, this is me. I'm just switching programs here. Hopefully you can still hear me. And there we go. So I'm on with the GoToWebinar here. So thanks again for everyone paying attention to this. And I've got a ton of questions. So I will almost certainly have to follow up on email because we got 20 or 30 solid questions here. Thank you so much again for making it through a 45-minute presentation on this. And I'm going to try to answer these in the order they were received. Hopefully the people who asked them originally haven't logged on. The recordings and the slides will be available as soon as possible, hopefully within the next week. I realize I'm asking you to click on links that are only showing up on video for you. Let's see. So, and I apologize again in advance for butchering anybody's name here, but Mr. Kreshchuk is asking to describe the latest in SIRS and TERS, and that's surface enhanced and tip enhanced Raman spectra. So those are both methods for enhancing the Raman cross-section using some kind of basically little antenna junction, some way of adsorbing or placing molecules into little pockets, basically that enhance the Raman scattering. We're hopefully going to talk about that in some small amount of detail at our next session. It's definitely an interesting application, really a powerful field, powerful tool for enhancing or for getting around one of the main problems of Raman scattering. One of the main limitations is that it's a fundamentally weak process. So these are ways of enhancing the field. Well, different mechanisms are proposed. My understanding is it's ways of enhancing the field strength, electric field strength that the molecule is experiencing. We'll talk about SIRS and TERS next week with applications. Let's see. A question from Mr. Traore, or Ephraim Traore. I'm so sorry for pronouncing it. I'm sure wrong. When acquiring resonance-enhanced Raman spectra, how do you combat fluorescence? And we'll talk more about resonance Raman spectra, resonance Raman spectroscopy, another method for not only selectively exciting the chemical that you're looking for, the species that you're looking for, but also massively enhancing the Raman scattering effect, getting some things that almost are more fluorescence-like out of it, breaking some selection rules. It's a whole world unto itself. But long story short, resonance Raman, which he's asking about here, is when you excite, when you hit your thing that you're looking at with a laser that has some overlap with the absorption of that, an absorption of that chemical. So he's asking about how do you combat fluorescence? And like I mentioned, there's the strange and complicated way of catching the Raman in the time domain before the photoluminescence comes out, before fluorescence comes out. Usually, typically, what people will actually do is just use a wavelength that is moving away from the fluorescence. If you're talking about resonance Raman, then of course you're going to be moving off of the absorption that you're trying to excite into. So that's not always the right way. When we say, oh, just move into UV or move into NIR, well, then you may no longer have that resonance that you're looking for. We'll probably talk more about that next week. But again, that's not a trivial question. It's a good question, which is why I can't answer it in a short amount of time. And I apologize for my inconsistent use of the laser pointer. I'm just so excited. I don't always remember to hit the control button or whatever it is that activates it. Another question about acquiring Raman spectra at low temperature, so liquid nitrogen temperature, 77 Kelvin, using a cold finger dewar. I've seen an even greater amount of fluorescence than at room temperature. Are there any tips to minimizing fluorescence at such a low temp? Again, it's ideal if you're working in a system that just doesn't fluoresce that much. And I was showing you some Raman and very weak photoluminescence spectra from a system, a donor acceptor system I was working with some years ago. And there, if you're adding something that can actually quench the fluorescence, then that's just fantastic, because then you have that taken care of. At the same time, then you have the potential for that interacting with what you're trying to study. So some sort of quencher might be an option. Let's see, what other things would I potentially look at? Other than trying to get spectrally your Raman to no longer overlap with your fluorescence, that's the main tool in the toolbox. Oftentimes is just if you can, move your wavelength, and if you can't, that's a tough problem. Another question from Amit Meller on the web. If Raman brightness is 1 million or 1 billion times weaker than fluorescence, do you need huge integration times to obtain Raman spectra? Oftentimes you do, unfortunately. Can it be used? Not always. Can then it be used for dynamic processes in chemistry and life sciences? It can be. Raman mapping, where you're moving around a sample, maybe confocally, and exciting or getting a Raman spectrum from each point, that can take a long time. Oftentimes you're just limited by the cross section, by the strength by the amount of the light that you send in that's sent back. You can always turn your power up to make things go faster. At a certain point, you might just start to melt or fry your sample by basically holding it, under a magnifying glass in the sun. So there's a limit to how much you can turn the power up simply to get more photons. So it may be the point that you're just limited in terms of acquisition time, integration time. So I've never really seen regular non-resonant Raman spectra done on a very fast, millisecond, sub-millisecond, something like that, tens of milliseconds. That can be challenging. But if you do something like, I think we name dropped that before, but surface enhanced Raman, tip enhanced Raman, or at the very least resonance Raman, you get a tremendous amount of enhancement in the strength of that interaction. It's a slightly different interaction at that point, a slightly different spectroscopy, but there are ways to enhance the strength of the Raman effect that we'll talk about next week, next 2 weeks, the next session. You'll get a reminder on applications. So that's a great and very perceptive question, because I'm talking about, I'm saying, oh my God, I'm trying to scare you. This is such a weak process. it's so pitifully weak. It doesn't, you hardly get photons out at all that are undergoing the scattering. And then you might say, well, how do I do this in the time domain? How do I get a reasonable cross section out? How do I get light through? So other than simply being good with efficiently getting light in and efficiently getting light out, that we'll talk more about that. But again, that comes down to equipment and technique, which will hopefully be addressed during our more application-centric next week session. Now that we've had some time to warm up, it's great getting all these questions. I want to integrate this into next week to drive some of that discussion. Could you recommend some algorithms or software for isolating the Raman and luminescence? Off the top of my head, I can't. We did everything, or I've always done everything arduously, manually in, for not first principles, but manual fitting in Igor or in SciPy or something like that. So I need to think about that. What's a good solution for that automated isolation? If they're too mixed up, it can be very difficult. But it might be if there's some separation, or if like I showed you in the example, if there's some peaks riding on a high background, then that could be as simple as fitting multiple Gaussians to extract that. But again, let me make a note to look into that as far as software goes. Is there a way to block the Raman signal and use laser excitation extremely close to the PL signal? If you don't mind just sending me George Kormalakis, if you don't mind just sending me an email clarifying that question. I think I might be misinterpreting it because I'm not exactly sure what you're asking. Send me an email, a.wise@andor.com. Galvu, I apologize for butchering. For benzene, can you show the IR and Raman active and inactive bands? Because the molecule has an inversion center, and I learned that IR active and Raman inactive and reverse. I zipped through that slide way too fast, but I had the Raman and the IR spectra superimposed, and you can see as one goes up, the other goes down. It's really nice to see those selection rules in effect. And again, if you want to know more about that, I would recommend maybe symmetry and spectroscopy. I'll have a book or a suggested reading list at some point here with stuff if you want to go deeper, because surely this couple of hours isn't going to be enough, like I mentioned, to replace an actual course or an actual book. Do Raman spectra change when your concentration goes down near zero? Can concentration be measured, evaluated with Raman scattering at low concentrations? That feels like a quiz question. Like I'm going to get graded on that one. It should be a Beer's law kind of thing normally, if there's no, in my opinion, if there's no molecular interaction happening. I could imagine there being a pretty strong nonlinearity if you have aggregation, like if you have your stators are floating around in solution, and at a certain concentration they start to clump, aggregate, dimerize, polymerize, whatever. But under normal circumstances, they ought to be linear. It all ought to be linear, I think. The concentration being proportional to the strength of scattering, or the total amount of scattering. You may know something I don't. So please let me know if I'm missing something about the question. A question about Raman LiDAR. I'll try to include some of that in next week's applications, or next 2 weeks. I apologize. I keep saying tomorrow. Next week, I believe it's in 2 weeks, you'll get a reminder. Is the detector for Raman always placed at 90 degrees to the incident radiation, or at any place? So in epi Raman, where you're looking with a microscope lens and your excitation is following the same path as your light collection, then they're both something like 180 degrees. 90 degrees is one thing. I sort of just showed my detector off at an arbitrary angle. There are so many collection geometries, and it doesn't have. I don't think 90 degrees would make sense for most samples. Usually, it's going to be looking normal to the surface or a little bit off. But again, there's so many different versions of the experiment. There's stuff like spatially offset Raman, where you're looking at a different point than you're exciting, and maybe we'll have some time to talk about that next week. And I apologize, I'm already running out of time. There's just one or two more good questions I wanted to address. Is there any big database with Raman shifts of elements and chemical compounds? I should have a go-to recommendation for that. I don't. I've always worked off of an eclectic mixture of cheat sheets, the NIST webpage, reference books, but I should know, and I will try to find out what would be, if you had to list one source to go to, what it would be. I got to look into that. That's a great question that you should get a good answer to, and I don't know what it is offhand. Could you please tell me what the omega V term represents? That would have been the vibrational frequency of the molecule that I was talking about, and I should have had that clear in the slide. How can the PL be avoided while taking the Raman spectra? We're going to talk about that next week, but there's a ton of different, well, several different options to do that. Raman and resonance Raman, we'll dip into that, and if you want to hear endlessly about it, come to the 4th episode of this short course. Let's see what else we got here. And I'll try. I got about halfway through the list, and I burned through, I think, my question and answer time. Thank you guys so much for the engagement. Thank you all so much for the engagement, for actually listening. I'm blown away that you were able to give me 45, more than an hour now of undivided attention. That's amazing, and I appreciate it. And I will really try to polish up my slides next time for all these, to integrate all these great questions. Hopefully the answers to all these great questions, but at least to address them. Am I out of time? Let me see if I'm going to get beeped off here. Oh, I got 5 more minutes. Let's see. For what types of molecular species are the anti-Stokes frequencies relevant? Said differently, what about a species leads it to have anti-Stokes frequencies? So here's my off-the-cuff response. That's a great question, because I kept saying, I was very hedgy about saying anti-Stokes, like in theory you get this, sometimes you might get this, very, very rarely you get this. So one thing I didn't show was the cartoon diagram where you have, the vibrational, the ground state vibrational levels or whatever, and then we excite to a virtual state, come back down onto one of the higher ground state vibrational levels, or higher vibrational levels. So you can draw these diagrams that show you coming up and then back down to a higher level, or from a higher level back down. So if you want, I'm rambling here. If you want to gain energy, if you want to donate energy to the laser from the molecule as it vibrates, then that vibration has to be excited in the first case. So for very, very low frequency modes, there's a possibility that it might already be vibrationally excited. For something that's like 1,000 wave numbers, the chances of that being normally excited, like in a laboratory atmosphere and like not on the sun, is very low. If you work out what the probability of, or what the equivalent kind of like temperature would be to have those, this suite of anti-Stokes lines actually show up, it would be crazy. So at room temperature, or at reasonable temperatures, generally the only anti-Stokes lines that you see, or anti-Stokes peaks that you see, are very, very low frequency. I apologize if I'm missing something, and I hope someone comes out of the woodwork to tell me that I'm wrong. That would be awesome. But I believe that's the case. You can do Raman thermometry with that. So anything that's Raman active should, in theory, can show Stokes and anti-Stokes bands, but to get high energy anti-Stokes bands to show up, you'd have to be at a crazy temperature. So we do see anti-Stokes lines, bands. I use lines, bands, vibrations, etc. interchangeably. I should be more clear. So it's not that certain molecules show or don't show them. I think it's more so that they're difficult to measure, not only because of the temperature, not only because of the energetic concerns, but also because the equipment that you need to measure it is a little more involved than to do the Stokes measurements, the Stokes lines measurements. So you'd have to have some way of looking on the higher energy side, very, very close to the laser. And I'll go into the technical details next week of why that's a total pain. So great question. And I used up the rest of my time answering that one question. I'm so sorry. All right, let me just see if all right, so I'm getting told that my time and my extra time is up. Again, if I didn't get your question, I'm sorry. We just got a really awesome amount of questions, really awesome amount of awesome questions. I look forward to seeing everybody at the next session. Check your emails for a reminder, and I'll answer offline. Thanks again, everybody. Have a good day, and I'll talk to you again soon.